In this video, we're going to actually try and look at the derivation of the path of the projectile. So derivation of the equation of the path of the projectile. As you can see, and as I've just discussed before, it takes the shape of a parabola, which you may know as a quadratic function. As you can see, in this case, it's likely to be an inverse quadratic function, i.e. negative x squared. But as this goes through, we'll have a look at that and see what comes out. Now, obviously, what we're trying to find is a specific point in space that we can link together to form some kind of Cartesian equation, i.e. an equation in terms of x and y. So once this object has been projected after a certain period of time, it'll be at some point x, y at time t. Now, x obviously is a horizontal displacement and y would be a vertical displacement at any particular time t. So if I go back to my basics and I look at my horizontal components and I create a suvat, you can see that we have a way of calculating an x displacement. So my displacement would be displacement in the x. U is u cos theta. V we don't know anything about. A is 0 because if you recall from the very first video, there is no acceleration in the horizontal, only in the vertical. And t we'll just set as a time t. Now obviously we have SUA and t, so applying S equals ut plus a half at squared, we can see that S would just be x, and it will equal ut, u cos theta times t. That's because a is 0, so the half at squared would 0 out. And we've seen this component before in previous videos. If I now look in my vertical and I apply suvat again, we have a few more elements, and not many. So obviously S is our displacement in the y. U is u sine theta. V we don't know anything about. A is now minus g, because remember all the acceleration happens in the vertical and we've used upwards as positive, so acceleration is downwards negative, and we're just going to take a generic time of t. And here we've got SUAT again, so I'm going to use S equals ut plus a half at squared, and that's going to give me a displacement in the y is equal to u sine theta times t plus a half of minus g t squared. Now what we've got here is we've got two equations, x and y, and they're both linked by this third variable t. Now these are what are called parametric equations, and what we can do is we can eliminate the t by using one of the equations and substituting it into the other, and that should give us our Cartesian equation in terms of x and y. Now I think the most obvious one to rearrange in terms of t would be our horizontal component, and from that we can see that t will equal x over u cos theta. And I'm going to take that and I'm going to sub it into there, because remember our t values are common throughout, the time and the x and y are common throughout. So y will therefore be equal to u sine theta multiplied by x over u cos theta plus a half of minus g and x over u cos theta squared. So if I take that now and I just look at simplifying it a little bit, y will be equal to, well, our u's cancel, and we also should know from unit 1, I think, sine theta over cos theta is tan theta. So u is equal to tan theta times x. Then we've got this here, which I'm going to just call minus g over 2 times x squared over u squared cos squared theta. Now obviously I could have left that in the brackets if I wanted to. So that's one way of writing it. If you notice now, I've got an equation of y in terms of x, and more importantly you can also see that it is a negative x squared, which would fit with our shape of our parabola. So one way of writing it would be like that. Another way would be to actually just put it back in the brackets, so we have tan theta times x, or x tan theta, whichever way you want it, minus g over 2 brackets x u cos theta squared. Now again, you may well be asked to derive the equation of the path, so it might be worth making some notes on this as well.